Now remember, rotational symmetry means that we rotate about a fixed point and we get the same shape in the end. So in all of these examples, I'll try and draw a center as well as possible. That won't exactly be in the center, but just bear with me there. I'll draw everything in the center, and that's the fixed point I want to rotate about, because I want to end up with the same shape on the other side. Now, not all of these might necessarily have rotational axes of symmetry. What you really have to find out is, say, how many degrees did I rotate? So that's the most important part. So the question is, when I rotate it about this point, assume it's the center of my shape, do I end up getting the same shape in the end, depending on some number of degrees of rotation? So I'll go ahead and take this, and as a square, I can rotate it 90 degrees, and I'll get a square again in the same exact area. Of course, they'll all be squares, but you want to make sure that each point hits right where the other one was. 180 degrees. So this has rotational symmetry if I go 90 degrees clockwise or counterclockwise, like so. And if I go 180 degrees. So for instance, another way of putting that is it has rotational symmetry right here and all the way around right here. And of course 90 degrees counterclockwise as well. But that's just how I'm putting it. This is the point that I'm rotating about, and here's the angle that I rotate it with. Because remember, I am rotating it about the center, even though it looks like I'm dragging it from the top. Now, triangle is kind of the same thing. You're just going to rotate it until you figure out, well, how do I get a triangle again with a horizontal bottom and a base at the tip, just like a pyramid? So I'll rotate it, and I'll keep going. Now, 90 degrees doesn't give it, and it doesn't go until right there. Now, keep in mind here, I'm not actually rotating about the center, so this is kind of my fault. You can see I should be rotating about there, but right here, I rotated this amount of degrees, and so you have to figure out what that is. Remember that this vertex started up here, and it went about the center, and then it went down here. So how many degrees is that? So you might have to figure this out by using old geometric ideas here. Consider this to be an equilateral triangle. So all these sides are congruent. If that's the case, all of these angles are 60 degrees, and 60 and 60. So if all of these are 60, and this ends up bisecting that angle here, then that means this is 30, and that means this is 30. So what's this angle here if this little triangle here adds up to 180 degrees? 30 plus 30 is 60, and 180 minus 60 is 120. So this angle here is 120 degrees, and that's how many degrees this thing rotated. Okay, so about this central angle right here, or well, I'm sorry, about this fixed point, which it supposedly rotated about, this went 120 degrees clockwise. And if I kept going, I could do another 120 degree rotation. Obviously, I'm not orienting this perfectly. Let me get this exactly where it should be. And there's another 120 degrees. So this has this can rotate 120 degrees, and it has rotational symmetry in that. So its angle of rotation is 120 degrees. Now, it doesn't have 180 degree rotation, so that means this does not have point symmetry, whereas this one does. Okay, here's another parallelogram, and if I rotate it again, if I rotate it this way, you can see I don't end up with the same parallelogram, but if I rotate one more time, 180 degrees, I get it again. So that was my initial example right here, And if you do 180 degree rotations, then you have your parallelogram, which has rotational symmetry. A pentagon, so this is more like the triangle, where I have to get a vertex at the top and a horizontal line on the bottom. So when I rotate this many degrees, it ends up having rotational symmetry. Now, how many degrees is that? So that's, again, something you'll have to be able to figure out in your own special ways, using geometry or using earlier things that you know. Keep in mind that the exterior angles of a, well, I can't draw it out there, but the exterior angles of a regular polygon, or well, of any polygon, add up to 360 degrees. So all of these here add up to 360. And there's obviously one right there. So if there are 5 of them, 360 divided by 5 is 72 degrees. And if that's 72, I apologize for that. If that's 72, and this is an angle bisector right here, this red marks an angle bisector, and that means this part ends up plus 72 ends up equaling 180. So 72 plus 2 of these angles, which I want to find out, because I want to find out what this one particular angle is. Plus 2x is 180. So 2x equals 108. So x is 54. So if that's 54 degrees, and this is 54 degrees, then this central angle ends up being 72 degrees. Now, that's something which you might have noticed over here. I should have used exterior angles again. You can presume here that your exterior angle is congruent to your central angle of your regular polygon. So same with this here. If this is 60 degrees, and this is 120, just like my central angle right here. And a star kind of works the same way. If I rotate this many degrees, and there are 5 points in it, this many degrees to go that way, I need to say how many degrees did I rotate. The star is a little different though, because I only have points to look at and not so much sides, but consider everything to be inscribed in a circle. So if I have a circle that surrounds it, like so, the circle has this central angle to look at, much like this has this central angle to look at. Now these are the same central angle because they're all congruent and they all divide evenly by 5. So that's really what you're going to have to look at here and say, where does it divide into? Now, neither the Pentagon nor the star have point symmetry, but all these central angles here are 72 degrees, just like this one here. These are all 72 because they all divide into 5 congruent central angles. I'm sorry for making this pretty rough here. The trapezoid. Can I rotate this trapezoid any which way so that I end up with this shape just like this? Let's go about 45 degrees, 90 degrees, 180. Nope. And if I've gone past 180, then that means I haven't found any sort of way that I can do this. So I can keep going and show you I won't get one. But once you go past 180 degrees, you'll realize it doesn't quite matter. So actually, when you say clockwise or counterclockwise, it's almost irrelevant. If I say 90 degrees clockwise, that also means 90 degrees counterclockwise. That's the only possible way you can have rotational symmetry and make that happen. And finally, the hexagon. Much like the Pentagon, if I want to end up with this horizontal line up at top and at bottom, I'll rotate it until I find that. Okay, so there's the point. And it rotates this much every time. From here to here. So much like the circle, as I said, you wouldn't really have to do all the central angle or all of this external angle stuff. The important thing is just the central angle. Figure out what the central angle is. And in this case, this divides into 6 equal portions. And these 6 equal angles should add up to 360. So I do 360 divided by 6, and I find out this central angle is 60 degrees. So every 60 degrees I rotate, this has rotational symmetry. Now it also has point symmetry because I can rotate this 180 degrees and end up also having a boom like that. I can also have a symmetrical shape, much like the other one. I'm sorry, a congruent shape, much like the other one. A lot of brands and logos also have line or reflectional symmetry, and I should have said as well as reflection or rotational or point symmetry. Now, line and reflectional symmetry are the same thing. Rotational and point are not. So these are 2 different concepts. The fact that I just had them in slashes just meant that they're part of the same thing. Point means 180 degree rotation. Now the X and X box, it has line symmetry only at one point. I'm sorry, only across one line. And that is, I'm not quite sure why that's happening. And that is right there. Crosses right through. I have a reflection here and here. And I think that's it. I can't rotate it anywhere and give this congruent X because this is not a congruent X in itself. This circle here, now, like I said, circles, if this were a perfect circle, normally has line or reflectional symmetry all the way around. But if I cut across here, I did not make a reflection from this side to that side. Right? All these white lines should end up looking down there to be a reflection. So there are only really a couple of lines of symmetry. There's one right here if I divide right down the middle, making a reflection, and one right across the middle horizontally as well. And if I drew those perfectly, obviously I'd end up getting that. So this only has 2 lines of symmetry here and here. You can practice with some other ones here. The Starbucks, again, straight down the middle. It's rough sometimes to give the examples that are only right down the middle because